Today we are going to discuss about impulse response for LTI system. So first one is impulse response. If the input to the system h of t in continuous time and h of n in discrete time is the impulse, that is delta of t in continuous time and delta of n in discrete time, then the output or response from the system is given as delta of t to h of t, which will give you the value delta of t convolution with h of t, which is equal to h of t. If we take for discrete time system, delta of n is the input for h of n, and we'll get answer as delta of n convolution with h of n, which is equal to h of n. That means for continuous time signal we have to consider impulse response as delta of t, and for discrete time signal we have to consider the input as delta of n. Next, we are going to discuss about properties of LTI systems with respect to impulse response. System behavior is characterized by impulse response. This characterizes the input-output behavior of LTI systems. Consider two LTI systems with impulse response h1 of t and h2 of t connected in parallel as shown in the diagram. X of t is the input, h1 of t and h2 of t are the impulse responses connected in parallel connection, and output is y of t. The output of this connection of systems y of t is the sum of the outputs of each of the system, that is shown in the second diagram. X of t is the input and output is y of t. Y of t is equal to h1 of t plus h2 of t. Then y of t is equal to y1 of t plus y2 of t, which is equal to x of t convolution with h1 of t plus x of t convolution with h2 of t. Then y of t is equal to integration of minus infinity to infinity x of tau into h1 of t minus tau into d tau plus x of tau into h2 of t minus tau into d tau. Combining the integrals, we have the impulse response of two systems connected in parallel is the sum of the individual responses. That is, y of t is equal to integration minus infinity to infinity x of tau into h1 of t minus tau plus x of tau into h2 of t minus tau into d tau, which is equal to minus infinity to infinity x of tau into h of t minus tau into d tau, which is equal to x of t convolution with h of t, which is equal to x of t convolution with h1 of t plus x of t into convolution of h2 of t, where h of t is equal to h1 of t plus h2 of t. Next, we are going to discuss about cascade connection of system. Consider two LTI systems with impulse response h1 of t and h2 of t connected in series as shown below. h1 of t and h2 of t are connected in series with x of t as input and z of t is the output of first system, and that is the input for the second system, and the final output is y of t. Then first property is, let z of t be the output of the first system and the input to the second system in cascade. The output y of t is expressed in terms of z of t as y of t is equal to z of t star h2 of t, or y of t is equal to minus infinity to infinity z of tau into h2 of t minus tau into d tau. Z of tau is the output of the first system expressed in terms of the input x of tau as z of tau is equal to z of tau convolution with h1 of tau, which is equal to integration minus infinity to infinity x of v into h1 of tau minus v into dv. Here, v is used as the variable of integration in the convolution integral. Then y of t is equal to integration minus infinity to infinity integration minus infinity to infinity x of v into h1 of tau minus v into h2 of t minus tau into dv into d tau. Put tau minus v as eta, then integration minus infinity to infinity, take x of v outside, integration minus infinity to infinity h1 of tau h2 of t minus v minus eta into d eta into dv. The inner integral is identified as the convolution of h1 of t with h2 of t evaluated at t minus v. Then h of t is equal to h1 of t convolution with h2 of t, then integration minus infinity to infinity h1 of eta into h2 of t minus v minus eta into d eta is equal to h of t minus v. Substituting this, we get y of t as y of t is equal to integration minus infinity to infinity x of v into h of t minus v into dv, which is equal to x of t star h of t. This obeys the associative property of convolution, that is x1 of t star h1 of t star h2 of t is equal to x1 of t star h1 of t star h2 of t. The impulse response of two LTI systems connected in cascade is the convolution of individual responses. Next, we are going to discuss about second property. Let h of t is equal to h1 of t star h2 of t. H of t is equal to integration minus infinity to infinity h1 of tau into h2 of t minus tau into d tau. Performing the change of variable v is equal to t minus tau to obtain h of t is equal to integration minus infinity to infinity h1 of t minus v h2 of v into dv, which is equal to h2 of t convolution with h1 of t. This is known as cumulative property of convolution. Convolution of h1 of t and h2 of t can be performed in either order. This corresponds to interchanging the order of the system in the cascade. Discrete time systems and convolution have identical properties to their continuous time counterparts. Next, we are going to discuss about properties of linear time invariant system. So first one is memoryless systems. Output of a memoryless system depends only on the present input. Exploiting the cumulative property of convolution, the output of a LTI discrete time system may be expressed as y of n is equal to h of n convolution with x of n, which is equal to summation k is equal to minus infinity to infinity h of k into x of n minus k. For this system to be memoryless, y of n must depend only on x of n and cannot depend on x of n minus k for k not equal to 0. This condition implies that h of k is equal to 0 for k not equal to 0. Hence, a LTI discrete time system is memoryless if and only if h of k is equal to c into delta k, where c is an arbitrary constant. In continuous time system, the output can be written as y of t is equal to integration minus infinity to infinity h of tau into x of t minus tau into d tau. A continuous time system is memoryless if and only if h of tau is equal to c into delta tau, for c is an arbitrary constant. For example, consider the LTI system of pure time shift. Y of t is equal to x of t minus t naught. For values of t naught is equal to 0, the system is memoryless. For t naught less than 0, t naught greater than 0, the system has a memory. The impulse response for the system can be obtained by taking input equal to delta of t. Then output y of t is equal to h of t, which is equal to delta of t minus t naught. Therefore, x of t minus t naught is equal to x of t convolution with delta of t minus t naught. The convolution of a signal with a shifted impulse simply shifts the signal. Next, we are going to discuss about causal systems. The output of a causal system depends only on past or present values of the input. Y of n is equal to summation k is equal to minus infinity to infinity h of k into x of n minus k. Past values of input are associated with indices k is greater than 0 in the convolution sum. Future values of input are associated with indices k less than 0 in the convolution sum. In order for the system to depend only on past or present values of the input, we require h of k is equal to 0 for k is less than 0. Hence, for a causal system, h of k is equal to 0 for k less than 0, and convolution sum is rewritten as y of n is equal to summation k is equal to 0 to infinity h of k into x of n minus k. A causal continuous time system has impulse response that satisfies h of tau is equal to 0 for tau less than 0. The output of a causal system is thus expressed as the convolution integral y of t is equal to integration 0 to infinity h of tau into x of t minus tau into d tau. For example, the system h of t is equal to u of t is causal, but the system h of t is equal to delta of t plus t naught for t naught greater than 0 is non-causal. In general, a signal x of t is called as causal signal if x of t is equal to 0 for t less than 0. The signal is anti-causal if x of t is equal to 0 for t greater than or equal to 0. Any signal that does not contain any singularities, that means a delta function or its derivative at t is equal to 0, can be written as sum of a causal part x plus of t and anti-causal part x minus of t. That is x of t, we can write it as x plus of t plus x minus of t. Next is stable systems. A system is bounded input, bounded output, that is VIBO stable if the output is guaranteed to be bounded for every bounded input. The magnitude of the output is given by magnitude of y of n is equal to magnitude of h of n convolution with x of n is equal to magnitude of summation k is equal to minus infinity to infinity h of k into x of n minus k. Since the magnitude of a sum of numbers is less than or equal to the sum of the magnitudes, then magnitude of y of n less than or equal to magnitude of summation k is equal to minus infinity to infinity h of k into x of n minus k. Since the magnitude of a product is equal to the product of the magnitudes, the magnitude of y of n is less than or equal to summation k is equal to minus infinity to infinity magnitude of h of k into magnitude of x of n minus k. If x of n has a finite value mx, that is magnitude of x of n less than or equal to mx less than infinity, then magnitude of x of n minus k is less than mx. Magnitude of y of n less than or equal to mx summation k is equal to minus infinity to infinity magnitude of h of k. Hence, the output is bounded. Magnitude of y of n is less than infinity provided the impulse response is absolutely summable. That is, summation k is equal to minus infinity to infinity magnitude of h of k less than infinity. In case of continuous time, system is VIBO stable if and only if the impulse response is absolutely integratable. That is, integration of minus infinity to infinity magnitude of h of tau into d tau less than infinity. For example, consider a system that is a pure time shift in either continuous time or discrete time. In continuous time, integration minus infinity to infinity h of tau into d tau is equal to integration minus infinity to infinity magnitude delta of tau minus t naught into d tau is equal to 1. In discrete time, summation n is equal to minus infinity to infinity magnitude of h of n is equal to summation n is equal to minus infinity to infinity magnitude of delta of n minus n naught equal to 1. Both the systems are stable. Consider the accumulator in discrete time. Summation n is equal to minus infinity to infinity magnitude of u of n is equal to summation n is equal to 0 to infinity magnitude of u of n is equal to 1 by 1 minus 1 which is equal to infinity. That is, according to geometric series, summation n is equal to 0 to infinity r power n is equal to 1 by 1 minus r. Similarly, integrator in continuous time, integration minus infinity to infinity magnitude of u of tau into d tau is equal to integration 0 to infinity 1 into d tau which is equal to infinity. Hence, both the systems are unstable. Next is unit step response of LTI system. The response of a LTI system to a step input characterizes how the system responds to sudden changes in the input. The unit step signal is used quite often in describing the behavior of LTI systems. The unit step response S of n or S of t corresponding to the output when x of n is equal to u of n or x of t is equal to u of t. From the convolution sum representation, the step response of a discrete time LTI system is the convolution of the unit step with the impulse response, that is S of n is equal to U of n convolution with H of n. By commutative property of convolution, S of n is equal to H of n star U of n, and therefore S of n can be viewed as the response to the input. H of n of a discrete time LTI system with unit impulse response. If U of n is the unit impulse response of the accumulator, then S of n is equal to summation k is equal to minus infinity to infinity h of k. Therefore, h of n can be recalled from h of n using the relation h of n is equal to s of n minus s of n minus 1. The step response of a discrete time LTI system is the running sum of its impulse response. Conversely, the impulse response of a discrete time LTI system is the first difference of its step response. That is, S of n is equal to h of n convolution with u of n, which is equal to summation k is equal to minus infinity to infinity h of k into u of n minus k. Since u of n minus k is equal to 0 for k is greater than n, u of n minus k is equal to 1 for k less than or equal to n. Then S of n is equal to summation k is equal to minus infinity to infinity h of k. The step response is the running sum of impulse responses. Similarly, the step response S of t for a continuous time system is expressed as the running integral of the impulse response. Then S of t is equal to integration infinity to t h of tau into d tau. Unit impulse response is the first derivative of the unit step response. Then h of t is equal to differentiation of s of t, that is d of s of t divided by dt, which is equal to s dash of t.